So we're going to be going over what the formal definition of a limit is, and we're going to start by talking what is a limit. And a limit is, as x approaches a, for a function f of x, it will be approaching this value L. So we can graphically show this, which is shown by the graph to the bottom left right there with the hole, that as x approaches a from the right side, it's also going to be approaching L, and as x approaches a from the left side, it will also be approaching L. So what does this mean? We could write this in a more familiar way, which is limit as x approaches a of f of x equals L. So what is the formal definition of a limit? And in order to do that, we have to use something called epsilons, which is a Greek letter which represents y values, and deltas, which represent x values. So epsilons in general will tend to be greater than 0, and deltas will also tend to be greater than 0. It's just an easier way of writing it and easier to approximate the limits. So more or less, in a graphical sense, we can illustrate this by saying that the domain of the x values will be a minus delta and a plus delta. So we can also say that the y values will range from L plus epsilon and L minus epsilon, and we can say that f of a plus delta will be approximating L plus epsilon, and we can say that f of a minus delta will be approximating L minus epsilon. So in saying that, we are able to illustrate a range and domain where the limit can exist, and this illustrates a region between a minus delta and a plus delta that will illustrate how close you will be to the limit at L. So once again, this region will encapsulate this region right here. And because of that, we can go ahead and say that if x is within delta of a, then f of x will be within epsilon of L.
So given the statement, if x is within 1 delta of a, then f of x will be within 1 epsilon of L. So we can write this algebraically. So we know that it's going to be greater than 0, and we know that it's going to be the absolute value of x minus a will be less than the distance of delta. This is because we know it's going to be within delta. So given that, we can more or less say this statement. This statement also allows us to say then f of x will be within 1 epsilon of L. So we can say that f of x minus L, and take the absolute value of that, will be within 1 epsilon of that. So with these two equations, we can solve for the formal definition of the limit.
So we're going to go ahead and prove the statement that limit as x approaches 2 of 8x plus 4 equals 20. And the first thing we're going to do is we're going to assign our a, f of x, and L values. So a is 2, 8x plus 4 is f of x, and 20 is L. And since we know we are dealing with a limit, and if it is to be a limit that is true, we know that the absolute value of f of x minus L will be less than epsilon. So, given that, we can go ahead and plug in values from the original equation. So we're going to go ahead and plug in 8x plus 4 for f of x, and subtract 20 because of L. And that will be less than epsilon. So, from here we can go ahead and combine the like terms. So we'll get 8x minus 16 is less than epsilon. And at this point, we can go ahead and take out an 8, so we'll get absolute value of 8 times x minus 2. And then we know that it's a constant, so it's not going to affect the sign of the absolute value, so we can go ahead and take out the 8, and we'll get 8 absolute value of x minus 2 is less than epsilon. And we can go ahead and divide 8 to both sides, so we'll get the absolute value of x minus 2 is less than epsilon divided by 8. And so since it's a function, and if it is a limit, we know that delta and epsilon should be related in some way. So we're able to say that epsilon divided by 8 equals delta, since we know that 0 is less than the absolute value of x minus a, which is less than delta. So since we know this statement, this resembles a very similar resemblance to the last statement we have when we algebraically manipulate f of x minus L, the absolute value of that. So we can go ahead and say 0 will be less than absolute value of x minus 2, which is less than the epsilon divided by 8. So upon doing this, we can go ahead and algebraically manipulate. So we're going to go ahead and multiply by 8 to each portion of the inequality. So we get 0 times 8 is less than 8, absolute value of x minus 2, which is less than epsilon. And we can go ahead and say 0 is less than absolute value of 8 times x minus 2, which is less than epsilon. And from this point, we can go ahead and multiply the 8 times x minus 2, and we'll get 8x minus 16, taking the absolute value of that, is less than epsilon. And we can go ahead and split it up, so we can say that 0 is less than 8x plus 4 minus 16, or minus 20, which is the same as 4 minus 20, which is 6 minus 16. So we still have the same statement, we're just splitting it up. And from there, if we put 8x plus 4 in parentheses, we see that it resembles the original function f of x, and 20 is actually our L value. So because of that, we are able to say that the limit will exist because we know that in plugging in the relationship between delta and epsilon, we will revert back to f of x minus L is less than epsilon. Therefore, the limit of x approaching 2 of 8x plus 4 equals 20 is true and exists. Thank you. So common mistakes you could undergo are misunderstanding what the epsilon-delta limit definition is. So in order to solve this, you should be able to explain the same definition using values or different variables. Another big mistake is incorrectly writing general equations like 0 is less than the absolute value of x minus a is less than delta, or the absolute value of f of x minus L is less than epsilon. So more or less understand what the statements mean in words, and you'll be able to write it out properly when doing them. And miscomputing values, you should just make sure you write out each step, and the previous step is equal to the next step.